let's take the simplest game possible, which is of a tic-tac-toe, and let's try to say how will we make a strategy or a policy to play a tic-tac-toe. You know the starting state, which is your source, as simple as possible, which is the empty game board around over here. Now from this game board, what happens is, this is what I call as the source. From this game board, what happens is, first Max is expected to move, and therefore all the actions that Max could apply in the search will be the branches. So here is Max thinking, should I put across here, in which case the state of the game will be like this? Should I put across here, in which case this state of the game will be like this? Should I put across here, in which case the game of the state will be like this? Or I should put across here, the state of the game will be like this. Mind you, this is the simplest game possible. Look at the number of branches already. Now, what really goes around over here is that suppose I know what is the utility of each one of these. Of course, we'll recursively compute that up, and I know the utility of this is that I will definitely win. The utility of this is, so the utility of this is that I'll definitely win. Utility of this is I'll definitely lose. Utility of this is that I'll win. Utility of this is what I'll win. What Max tries to do is, it tries to take the action which maximizes the expected returns. And because it tries to maximize the expected returns, I say the utility of this state for Max is, I'll choose the action which maximizes my return. So maximum of +1, -1, +1, all the way up to a +1, which is a +1. That's how I model Max. That's how I model myself as a player who will constantly try to take an action such that the winning is maximized. Now, and once you do that, which action do you select? This is probably a good action to select because your chances are, of course, maximized. However, I just took a terrible shortcut, and in reality, we have nothing like that. So I will have to go back to all of these and try to see how do I really calculate each one of these values. So now let's try to think that how do I calculate utility of this state? Is there a way I could do that? Yes. Who is supposed to play min? Okay, by the way, sign convention, so that's Max. So who's supposed to play around over here? Min is supposed to play around over here. Wonderful. Now let's reverse it up. Let's think like Min. Let's think like your opponent. If you have to defeat your opponent, of course you do think like your opponent. And therefore, what all options does the opponent have? This X is fixed. It could be a O here. 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 And again, I'll assume that I somehow have the utility values. So let's say it's a -1, it's a +1, it's a 0, it's a +1. Now this is Min. Min is trying to maximize its own returns, in pursuit of which it is minimizing Max's return. So instead of a Max, I'll instead take a minimum of everything which is possible, which of course will turn out to be a -1. And this seems like to be a very good thing for Min to do. It's minimizing whatever it's doing. This has an assumption. It's obviously called as a rationality assumption or the optimal player assumption, which means you assume that the person whom you are playing with is an intelligent agent. It plays the best moves possible. It's the best player possible. It does all the calculation and makes the best move. And so are you. So you assume two grandmasters are sitting. You say, if I'll do this, opponent will do this. I'll do that. Opponent will do that. I'll do that. This will be the return. On the other hand, if I do this, the opponent will have to do this. I'll have to do this. These are the options of the opponent. The opponent will always select the best option possible. Now, obviously, it turns out that this game tree, also called as a search tree, is too big. It will not fit in the entire board. Believe me, even though when you actually compute that in your computer program, it will take absolutely no time. I've got big limitations of space and my own effort. Let's play a stupid game, which is the same tic-tac-toe, except for it's a 1x3 tic-tac-toe. And from now on, I'll draw the stage tiny. You can visualize it. So, and I'll draw it like right next to who is playing it. So that's my 1x3 tic-tac-toe. Only 3 actions possible, which is this action, in which case Max puts a cross here, this action Max puts a cross here, and this action Max puts a cross here. Min will play. Min has only 2 options. So the first option Min has is a nut over here. The second option Min has is a nut over here. And remember, I'm going depth first search because it's optimal in case of memory. So now again Max plays. So Max has only one option. In game sometimes it happens. There's only one option. And therefore, all that can happen is Max plays over here. Now this is called as a terminal state. Terminal, you cannot play the game anymore. It's terminated. Game will stop. Whichever tool you are using, the game will stop. There is no move possible. And I'll have the terminal utility, which is 0. It's known exactly by the game logic. So I cannot do anything around over here. So this Max has only one option. So it takes a maximum of all the options in life, one option. And therefore again, towards the side, whatever I write down will be the utility values for Max, which is just a 0. So now what I do is, of course, it's a depth first search. So I continue. Max, again, poor Max has only one option left, which is xx0. It's again a terminal state. And this time Max wins. So the scoreboard reads Max +1, Min -1. Good for Max. Max is excited. It won. So even though there was only one option, it takes max of all the options possible, which is just one option, and it gets a nice +1. Good for Max. So now I come to this Min. It's a depth first search. Min will take the minimum of the two. Now this 0 means that if Min takes this branch, it's gonna tie. But why would Min want to tie? But if Min takes this branch, Max will get a +1, Min will get a -1, will get a -1, so it's bad. And therefore what Min does is, it takes the minimum of 0 and +1, which is a 0. So that's a value around over here. The utility for Max is 0 of the state. The utility of Min is also 0 for the state. Now let's continue on the other branch. I'm going in a nice backtracking way. So this is what is my next branch. And let's see the options that I have. Of course, Min is supposed to play the next move. Min has two options left. The first option that Min has is 0x, and the second option that Min has is a x and a 0. In both cases, the next move will be played by Max. Max will have only one option, which will give the terminal state. So now I can go extremely quick, which of course gives a +1 to Max. Max is jubilant. I backtrack, I take the maximum of all the options available, which is just a +1 of Max. I again backtrack. So the second option possible is that, of course, Max plays this move, and the only thing which is possible is a XX and a 0, which of course still means that it's a +1 return for Max, plus Max will take all the options, only one, which returns a +1. Min will take a minimum of +1 and a +1. Bad. If Min takes this branch, it loses. If Min takes this branch, it loses. Now what a younger sibling would do, realize this, it's gonna lose, and say, I don't want to play. But then it's computer, you don't have the option to quit. So, you know you're gonna lose, so it's a +1. I'm playing for Min. Min took a minimum of both. It took a minimum of +1 and +1, which unfortunately was a +1. Now let's take the other branch as well really quickly. So that's my other branch. Of course, Min will play it. Min has two options. The first is 0 or nut cross, and the second one is a nut and a cross. In both cases, the next move will be by Max, which will be a 0xx. So Max wins. And in the other case also, it's a x0x. So in this case, it's unfortunately a tie. +1, max of all the options, 0 of all the options. Remember, it's still depth first search, so I should have solved this before going here. It's a min of +1, 0, which is a 0. So luckily, Min can force a tie over here. And what does Max do? It takes a maximum of 0, 1, and 0. So I have a maximum of 0, 1, and 0, which is a 1, and therefore my utility is 1. So let's see how this game will proceed. Max will definitely select this branch. It has the highest returns out of 0, 0, and 1. It has the highest returns. Max is gonna play this move. Unfortunately for Min, if it plays this, it loses. If it plays this, loses. It's already lost. So let's say Min plays this. It doesn't matter. You don't even know it, by the way. You don't know what will Min do. And Max will ferociously play this one. And guess what? Max will win because it's two crosses simultaneously. Bad game. Whoever plays first, whoever starts first always wins. Now, these are of course the utility values, and it's important to say what do these different values mean. So if for this particular thing the utility is S is equal to 1, that means Max is guaranteed to win. Yes, Max is guaranteed to win, irrespective of how Min plays. If Min plays beautifully, Max will win. If Min plays very badly, Max will win. It may win even better. So Max is guaranteed to win irrespective of how Min wins, of course, provided Max does not make a mistake. On the other hand, if for this particular game US is equal to -1, it means Max is guaranteed to lose provided Min does not make a mistake. Practically, that's what will happen. You're playing a game of chess, you know you lost, you'll still play it. You'll still play it because you have this inside. I know my opponent, bad chess player, will definitely make a mistake. You just wait for the mistake to happen. You play the best that you can, but you wait for the mistake to happen. So don't leave the game. If Min makes a mistake, Max will win, or at least enforce a tie. On the other hand, if US is equal to 0, so that means there is no guarantees. And of course, if both play well, which means that none of them makes a mistake, it will definitely result in a tie. So bad for the game. Both of them play well, it returns in a tie. So the above game was actually bad because even before you start playing it, you know that Max is gonna win it. Even before you start it, you know Max is gonna win it. Normally in games, the root will always be 0. That means unless and until one player makes a mistake, it is gonna end up in a tie or the game is fair. So both the players are equally likely to win or at least enforce a tie. That's a bad game, but of course I had very little space to deal with and therefore I had to do that up. Now, this particular thing, of course, it does raise a lot of questions, so I'll take them one by one. The first question is, of course, that do I really need a depth first search? You people also know it as backtracking. So yes, practically the games will be humongous. And you will not have the memory to store every possible outcome of the game. You're not going to do that. And because of that, you cannot store the complete game tree. It's impossible to do it. You will have to go with memory efficient searches, which is a depth first search. Now, I get a lot of immediate question, but you said that your policy or your output is the strategy pi s, which means a map that maps every possible state with an action, which means the memory requirement of this is the number of states possible, or practically the entire state space. And then you say that you use depth first search because you cannot store the entire state space. Are these two things contradictory? Most famous question that I get. Now, whatever depth first search that I showed you, you do it live when the other player is thinking about the move. You do it live. Or to make it simple, you observe the current game state and then you do a fresh search. You calculate only the best current action possible, which is this one. And for everything but the current action, you delete everything else. When the second player makes a move, then you'll make a fresh game tree. Why will you make a fresh game tree? Because you don't have memory to store the entire game tree. Fair enough. So, every time you do a fresh search, so you do a search, make a game tree, calculate your first move, then wait for the opponent to make a move. When the opponent make a move, you make a new game tree starting from here. You make an absolutely new game tree. You do an absolutely new search. Why? Because you don't have the memory to store the complete game tree. So, it's not an offline search that is really happening a day in advance, an evening in advance, or whatever. It is a search which is happening live. Now, In search, there was a tree search equivalent, there was a graph search equivalent, and I said, graph search, use it if you have memory. Use all the breadth first search and the uniform cost search and the A-star algorithm. If you don't have, use iterative deepening. You don't have memory to store in everything. What if you actually have a memory to store in that? Then you make a table which is very similar to the close. It's called as the transposition table, and it stores exactly the same thing. So it's a map, same as the closed used in the A-star algorithm with first search. So it stores the state, and of course it stores the utility value. So in a game tree, if you start doing this search, and you calculate the utility of this state S as, let's say, a +3, and surprisingly, what happens is, again, you get the same state S, bingo. What you have is a state which is already stored here. You look at it, +3, and you just copy +3 over here. There's absolutely no need to do a complete search. So, very common question. Practically, can I make in such a table? No. But on a more positive side, you know the important states of a game. You know the states more likely to repeat by game logic, by heuristic. Now I can just loosely use the term heuristic. So start storing in the moment your 8 GB RAM, 24 GB RAM, I'm not sure what's the kind of RAM you use these days. You can even use the hard disk. It's about to get over. Now you need memory management. Now you say, okay, I know which ones are important. I'll keep them. I'll delete all the rest.